So picture this. You order a brand new smart blender online.
Okay.
It shows up at your door 2 days later. You open the box, plug it in, and then you realize you just absolutely hate the color.
Oh, yeah. Like it totally clashes with the kitchen.
Right. It clashes completely. So, you click a few buttons on your phone, slap a return label on the cardboard, and drop the box off at some local shipping center.
And you're done with it.
Exactly.
Yeah.
A few days later, the refund hits your bank account. And for you, the transaction is over. You've completely washed your hands of it. But, and this is what's crazy, that drop-off isn't the end of the story at all.
No, not even close.
It's actually the starting gun for this entirely invisible, intensely complicated, backward-flowing industry.
Yeah, the sheer scale of what happens after a consumer rejects a product is just staggering. I mean, we are diving into some really fascinating supply chain research today that exposes this massive secret.
And that's our mission for this deep dive, right? To really explore that literal afterlife of products.
Right, because processing your return requires this completely distinct parallel universe of warehouses, logistics networks, and highly specialized labor.
It's not just a truck driving backwards.
No, exactly. We're moving away from that traditional linear model of consumption where you make something, use it, and then throw it into this magical void called away.
Right, because away doesn't actually exist.
Exactly. Today, what goes out must eventually, fight its way back.
So we're going to uncover the mechanics of how modern supply chains are trying to stop waste before it even starts, how they turn discarded junk into immense value, and why that simple act of returning a blender kicks off an absolute logistical marathon.
It really requires completely changing how we view the physical stuff that surrounds us because, well, before we can even begin to understand how things move backward through a global network, we first need to understand the fundamental logic of why supply chains even care about discarded items in the first place.
Okay, let's unpack this, because the research brings up this foundational concept called the waste hierarchy. And it's visualized as a massive inverted pyramid.
Right, so picture a triangle pointing downwards.
Got it.
The geometry there is key. So the widest part at the very top represents the actions with the lowest environmental impact. And as you move down toward that narrow point at the bottom, the negative impact just drastically increases.
Okay, so what's at that wide, desirable top tier?
One simple directive: reduce. Don't create the waste in the first place. Like, use fewer resources from the jump.
Oh, I see. So if an engineering team figures out how to make, say, a laptop casing 2 millimeters thinner without it breaking.
Right, without losing structural integrity.
Then they've basically prevented thousands of pounds of waste from ever existing. And it doesn't exist, you don't have to manage it.
That is the ultimate goal. But, when reduction reaches its physical limit, you have to move down to the second tier, which is reuse.
Like keeping it in circulation.
Exactly. Keep the item in circulation in its current form for as long as possible. Think of a wooden shipping pallet. You want to use that same exact pallet 100 times before it finally splinters.
Rather than building a brand new one for every single shipment.
Right. But eventually, things do break. And that pushes us down to the third tier, which most people know: recycle.
Okay, so that means physically breaking a product down to its raw components to make something totally new.
Yes. And then the pyramid gets a little counterintuitive. The fourth tier is recovering energy during disposal.
Wait, how does destroying something actually recover energy? That sounds
like an oxymoron.
Yeah.
Well, if a complex material simply cannot be melted down and reformed into a new physical product, a supply chain will look for secondary value. So perhaps that material can be incinerated in a very specialized facility to generate electricity for the grid.
Oh, wow. So you are destroying the physical matter, but you're actively capturing energy from the process.
Exactly. And finally, when you exhaust all of those options, you reach the absolute bottom tip of the inverted pyramid, the last resort.
Dispose.
Right. Putting the item into a responsible landfill.
Okay. To make sure I have my head around the mechanics of this, let me try applying it to something maybe a little closer to home.
Go for it.
Imagine you're trying to manage the food in your kitchen using this exact inverted pyramid.
Okay, like this.
So the top tier reduce would just be only buying the groceries you actually know you're going to eat. Like, don't overpurchase.
Yeah.
Catching the excess before it even enters your house.
A very clean way to look at it.
Then step 2, reuse, would be eating your leftovers the next day for lunch. You aren't altering the food, you're just extending its useful life.
Right.
Step 3, recycle, is where you take your vegetable scraps and toss them in a compost bin to create fertilizer for your garden. So you're transforming the material into a new input.
which perfectly mirrors breaking down industrial materials, yeah.
And then step 4, recover energy, might be, I don't know, capturing the ambient heat coming off your stove while you're cooking to warm up the kitchen in the winter. You extract secondary value.
Exactly.
And finally, step 5, dispose, is when you simply have to throw away like a plastic meat wrapper that can't be composted or reused. It just goes straight into the trash.
Right. And if we connect this to the bigger picture, that kitchen analogy perfectly illustrates the foundational logic of what the research calls the circular economy.
The circular economy.
Yeah. The goal of a circular economy extends all the way from the moment a raw material is extracted from the earth right down to its final disposition. The ambition is to drastically reduce what goes into the landfill by making sure that one industry's output seamlessly becomes another industry's input.
So instead of a straight line from a mine to a dump, it's more like a series of overlapping continuous loops. Okay, so we have this beautiful theory of a circular loop. But how does a manufacturer actually guarantee their materials keep circulating? I mean, once a television or a washing machine leaves the factory, it's entirely out of their hands, right?
Yeah, you hit on the main constraint right there. A company cannot wait until a product is broken in a customer's living room to figure out what to do with it. You can't just, slap a recycling sticker on a brick of glued together plastic and call it a day.
Right, it doesn't work that way.
No. The solution has to start at the very beginning, at the drawing board.
How so? How does the drawing board change the outcome?
Well, what's fascinating here is how the source material breaks down sustainable product design. It starts with something called the Bill of Materials, or the BOM.
The BM, okay.
Right. It's basically the exact recipe of components needed to build a product. A sustainable bill of materials mandates fewer hazardous materials and a higher percentage of recycled materials before the assembly line even turns on.
But wait, changing the ingredients doesn't necessarily solve the structural issue, does it? Like if you use this beautiful recycled plastic for a remote control, but then you glue the entire casing together with industrial adhesive to save time.
Right.
Nobody can pull that plastic apart later to recycle it again. Doesn't that just defeat the whole purpose?
It absolutely would, which is why sustainable design introduces this vital engineering concept, design for disassembly.
Design for disassembly.
Yeah, you avoid the cheap industrial adhesive, you use screws or, internal snap fits. You engineer the product specifically so that when it reaches the end of its life, a worker can easily dismantle it and sort the components.
So you're literally designing the product for its afterlife.
Exactly.
But that sounds incredibly difficult to orchestrate, especially since major brands rarely even build their own products anymore, right? They use hundreds of third-party suppliers and logistics companies all over the world.
Oh, yeah. It's a massive web.
So how does a brand actually force a factory in another country to care about snap fits or the waste hierarchy?
Through rigorous, legally binding partner policies. A major manufacturer will actually map their supplier contracts directly onto those tiers of the waste hierarchy we just talked about. They force compliance through strict procurement rules.
Let's ground that. How does a partner policy actually work in practice?
Okay, let's look at the reduce tier. A manufacturer might force their retail partners to radically change their customer service protocols.
Oh, interesting. Like how?
Well, before a customer service representative is allowed to authorize a return shipping label, they might be contractually required to spend, say, 5 minutes troubleshooting the issue with the customer over the phone.
Oh, because if the customer just, they don't know how to pair the Bluetooth or something, the rep can fix it instantly.
Right.
And you prevent a perfectly good item from being packaged up, put on a truck, and shipped backward across the country. You reduce the logistical waste entirely.
Exactly. And another fantastic example falls under the recover tier. Think about appliances that use refrigerants like industrial air conditioners.
Right.
A brand will write strict procurement contracts requiring their disposal partners to physically capture those harmful cooling chemicals during the teardown process.
Rather than just letting them vent into the atmosphere.
Right. And the brand will actively audit those partners to verify that the chemicals are being captured and repurposed.
Okay, wait. Let me play devil's advocate here for a second, because I'm looking at the economics of this.
Sure.
Engineering custom snap fits instead of using cheap glue, auditing international partners for refrigerant recovery, paying customer service reps to spend more time on the phone. I mean, this all costs a fortune.
It does.
If a business's primary goal is to generate profit, How does a manager justify buying a much more expensive, sustainably sourced material just to make recycling slightly easier, like 5 years down the line? It seems like it would destroy their margins up front.
You're totally right, and it is the biggest point of friction in adopting circular models. But the answer lies in a financial calculation called total cost of ownership, or PCO. Right. You're absolutely right that a sustainable material or a complex snap-fit design might have a higher unit cost on day one, but the initial purchase price is just the tip of the iceberg.
So what's lurking under the water?
The hidden long-term operational liabilities. Let's go back to that cheap, highly toxic adhesive you mentioned.
Okay.
If you use it to hold a product together, your initial assembly costs look fantastic. Your margins are great.
Right. Everyone's happy.
Exactly. But 3 years later, when that product inevitably breaks and is returned, you don't just have a broken product, you have a piece of regulated hazardous waste.
Oh, wow.
And the legal fees, the specialized transportation, and the strict environmental compliance required to handle and legally dispose of hazardous waste are astronomical compared to standard recycling.
So you aren't actually saving money with a cheap glue at all. You're just deferring this massive financial penalty until the product inevitably comes back to you.
Precisely. By calculating the total cost of ownership across the entire life cycle, companies realize that the expensive, eco-friendly snap-fit design actually ends up costing them far less in the long run.
Okay, that makes perfect sense.
Yeah.
So we've solved the material issue. The manufacturer uses the smart snap fits, they avoid the toxic glue, they enforce brilliant partner policies.
Right.
But that still doesn't solve unpredictable human behavior. What happens when a customer just decides they ordered the wrong size or the item gets crushed in transit and they ship it back?
Yeah.
What happens to the physical object then?
Well, that event triggers a completely separate, massive logistical operation. The formal term in supply chain management is reverse logistics.
Reverse logistics.
Yeah. It is defined as a complete supply chain dedicated to the reverse flow of products and materials for the purpose of returns, repair, remanufacture, or recycling.
The research actually uses a phrase for this that I found really compelling. It says, reverse logistics must never be an afterthought, and it actually calls customer service marketing in reverse.
I love that framing. It's brilliant. Traditional marketing exists to initiate the forward flow of a product out into the world, right?
Right.
Well, customer service acts as the catalyst for initiating the backward flow. And just like a forward supply chain, reverse logistics involves multiple distinct streams of activity.
Like the physical stuff moving back.
Yes, the reverse flow of the physical products, of course.
Right.
But you also had reverse information flows, so data about why the item failed, warranty status, defect codes.
Oh, sure.
And you have reverse cash flows, processing refunds, absorbing return shipping costs, calculating the loss of initial revenue.
Here's where it gets really interesting to me. I like to picture a global supply chain, like a massive, powerful river.
Okay.
Forward logistics is just floating boats downstream. The current is working with you. Everything is uniform, packed neatly in identical boxes on pristine pallets, heading from one factory to known retail destinations.
It's a very smooth process.
Right. But reverse logistics is like trying to engineer that same river to flow upstream. You are actively fighting the current. You can't just put the downstream boats in reverse gear. You need entirely new infrastructure to catch all these random, unpredictable items floating backward.
That is a great analogy. And the physical reality of fighting that current is incredibly intense. Think about it. A forward warehouse is highly automated and predictable.
Right. Our codes everywhere.
Exactly. A worker, or even a robot, picks a pristine barcoded box off a shelf and puts it on a truck. But in a reverse logistics facility, the environment is fundamentally chaotic. A worker receives a mangled, half-open box sealed with, layers of duct tape.
They don't even know what's actually inside or what condition it's in until they rip it open.
Exactly. And that destroys predictability. The unpackaging, the testing of the internal motor, the careful disassembly of the casing, these are highly specialized, intensely manual skills. You cannot easily automate the opening of a crushed box or the diagnosis of a weird humming noise in a blender.
Right. A robot can't do that.
No. The tasks are entirely different. Retrieve the item, transport it backwards, sort it, and figure out its ultimate fate.
Well, if the work is that specialized and chaotic, who actually manages it?
Okay.
Does a massive electronics brand really have their own warehouse full of duct tape boxes and diagnostic stations?
Some do build their own internal capabilities, but very often, because the skills required to fight that upstream current are so completely different, Brands contract this work out.
Oh, okay.
They might hand the entire reverse process over to specialized third-party or fourth-party logistics providers, known as 3PLs or 4PLs.
So external experts.
Right, experts who have spent years building the dedicated reverse infrastructure so the original manufacturer doesn't have to bog down their forward-moving assembly lines.
Okay, so what does this all mean in practice? Let's ground this massive system in reality. Imagine you, the listener, just returned that $400 smart blender we talked about at the top of the show. You dropped it at the shipping center. It flows upstream through the 3PL's transportation network, and it finally lands on a metal sorting table in a dedicated returns facility. Walk me through the actual flow chart of what happens the second that box is opened.
Okay, so the worker at that sorting table acts like a triage nurse in an emergency room. They follow a rigorous disposition decision tree.
Decision tree. Got it.
The very first question they have to answer is this item in acceptable condition? Is it part of a recall or is it defective?
Okay, let's say the blender is totally fine. It was never even plugged in. The customer just hated the color.
That is the best case scenario. The worker verifies it is pristine, it gets repackaged, and it takes the easiest path, return to stock.
So it goes right back into forward logistics to be resold.
Exactly.
But what if the customer returned it because the motor was completely dead? It won't turn on at all. Now we're in the triage zone.
Right. Now it flows down the defective path of the decision tree. The worker must immediately determine the next calculation. Can we repair the whole product?
Like, is it just a loose wire?
Yes. Is it a loose wire that a technician can solder in 5 minutes to make the blender whole again? If the answer is yes, it is routed to the repair process. Once fixed, it might be returned to the manufacturer or liquidated as a certified refurbished item.
Let's push it further. Let's say the motor is completely fried. It would cost way more to buy a replacement motor and pay the technician's hourly wage than the entire blender's even worth.
Then we drop down another level on the tree. The next calculation asks, can you reuse the parts?
Oh.
The blender as a whole is dead, but perhaps the heavy glass pitcher is in perfect condition. Maybe the digital display screen is flawless.
So you harvest it.
Exactly.
Okay.
If so, the blender is sent to a specialized teardown process to recover those specific parts. Those recovered components are then used to build or repair other blenders in the facility.
Okay, and what if the whole thing was run over by a delivery forklift in transit? The motor is dead, the glass is shattered, the screen is cracked, there are literally no usable parts whatsoever.
Then we hit the end of the line for reuse. The product enters the final disposition process, and this is where the waste hierarchy from the very beginning of our conversation comes back to dictate the outcome.
It comes full circle.
It does. The facility will determine if the shattered glass and plastic can be recycled. If not, can the materials be donated or sold for scrap? Or, as the absolute final option, must it be responsibly disposed of in a landfill?
Wow.
And this raises an important point about the sheer scale of operations here. Think about the massive systemic intelligence required at that initial sorting table.
Yeah, that worker is making incredibly complex decisions.
A worker is looking at thousands of random, unique product failures every single day. They have to instantly calculate repair costs, spare parts value, and recycling viability to route that single blender correctly down that flowchart.
And they have to do it fast.
So fast, because every second an item sits in a returns facility, it is taking up space and losing value.
It completely changes how you view a simple return. I mean, it is an operational marvel hidden behind a single click on your phone.
It really is.
So to bring this all together for everyone listening, let's distill the core takeaways from our deep dive into the afterlife of products.
I think the most vital takeaway is that waste is no longer viewed as an inevitable, tragic endpoint of consumption. In a modern supply chain focused on the circular economy, waste is understood as a design choice.
Right.
If a product ends up in a landfill, it is largely because it was engineered to end up in a landfill. Through sustainable design, better bills of material, and strictly enforced partner policies, supply chains are fighting to keep materials in circulation from the moment they are conceived.
And reverse logistics is so much more than just a delivery truck driving backwards. It's not just taking things back. It is an entirely parallel, highly specialized industry.
A massive one.
It has its own dedicated warehouses, its own distinct flow of physical goods and data, and its own intense manual labor requirements. It's the complex upstream machinery designed specifically to feed that circular economy and keep the waste hierarchy functioning.
Which means the next time you print out a return label, tape up a cardboard box and hand it over the counter, you aren't just getting your credit card refunded. You are personally kicking off a highly choreographed, incredibly complex, backward-flowing supply chain.
You're dropping a boat into that upstream river.
Exactly.
It is a completely different way to look at the physical stuff that surrounds us. And, it leaves me with one final, slightly provocative thought to mull over.
Let's hear it.
If supply chains continue to get perfectly efficient at reverse logistics and product design fully embraces the circular economy, where every single component is designed from the start to be disassembled, reused, or recycled endlessly, will there come a day when the very concept of trash ceases to exist entirely?
Wow. Now that is a truly circular thought.
Something to think about next time you make a return. Thanks for taking the plunge with us today. We'll catch you on the next deep dive.